All right, so welcome back to Math 140 Science, November 18th. This is the second class of week 12, so I have no idea what lecture number we're in, but probably around 21, 22, something like that. And before we begin, there were a couple questions. The first one is, what is the standard error? So what is standard error? So, there's different formulas depending on the scenario, but, in chapter 20, for example, we have that the test statistic Z, if we know sigma, is X bar, not Z, just the test statistic is X bar, try that again, X bar minus mu naught over sigma over root n, if we do know sigma, or X bar minus, that was horrible. I'll try that again. Your data point minus, wow, hold on. I'm just doing this. I'm just all over the place here. Let's do a confidence interval first. So the formula for confidence interval is X bar plus or minus Z star sigma over the square root of n, or X bar plus or minus T star S over the square root of n. Now, these are the formulas for the confidence interval in the case where we're trying to figure out what the mean is. And for hypothesis testing, we have our Z statistic is equal to our data point minus the assumed mean if the null hypothesis is true, divided by sigma over the square root of n, or our T statistic is R average minus the assumed mean over S over the square root of n. In all of those cases, the standard error would be those guys. Those are your standard errors. The standard error is essentially the standard deviation of the sampling distribution. Standard error is the standard deviation of the sampling distribution. That is what the standard error is. It's the standard deviation of the sampling distribution. So that's a definition. So that should answer your first question. What is the standard error? Even in the more complicated scenarios, whatever's taking the place of those four guys, depending on whether it's a confidence interval, hypothesis test, etc., that is your standard error. Okay? Yes, no, maybe so? All right. The other question was about the quiz. So I'm going to open up the quiz. This is Math 140 Science.
Or I think your question was for, I guess, the p-value. It was a p-value, yeah.
For which question?
You said it was a number that was between this and this, right? Do you
remember?
It's like a flower.
I can't remember which. I'm trying to find it right now, the quiz, to open it. But yeah, it said number to this number.
I mean, was it a confidence interval? I don't know what the question was.
Let me look for it.
Was it the mini quiz or one of the practice quizzes?
It was the mini quiz that we recently took.
So a mini quiz. Mini quiz 3. Most likely 37 of 43 students took it. So yeah. Okay, it looks like there were 8 questions. If I share my screen, might you recognize it? Is that possible? Yes, no, maybe so.
I found the question. Do you want me to read it to you?
Sure. What was the question?
It said, is there a difference in the amount of airborne bacteria between carpeted and uncarpeted rooms? In an experiment, 7 rooms were carpeted and 7 were left uncarpeted.
Oh, wait, hold on 1 second. Hold on. Let me share this again. So start again, please. Go ahead.
Oh. Is there a difference in the amount of airborne bacteria between carpeted and uncarpeted rooms?
Wait. Difference. Okay, go ahead.
In an experiment, 7 rooms were carpeted and 7 were left uncarpeted.
Hold on.
The rooms
hold
were
on, hold on.
similar.
Hold on. 7 carpeted and 7 uncarpeted?
Yes.
Okay, hold on. Okay, go ahead.
The rooms were similar in size and function. After a suitable period, the concentration of bacteria in the air was measured in the units of bacteria per cubic foot in all of these rooms. The data and summaries are provided. So the carpeted rooms, the mean of the carpeted rooms is 184, and then the standard is 22. And then uncarpeted, the mean is 175, and the standard is 16.9. And
Okay.
then it asks a 95% confidence interval for the difference in mean bacterial concentration in the air of carpeted rooms versus uncarpeted rooms using the conservative value of the degrees of freedom is, and then it gives you, do you want me to give you the options? Because I don't understand how.
Well, the degrees of freedom is 6. You agree with that?
Yeah, but I didn't get what I was looking for when I saw these answers. I was like, am I looking for the degrees of freedom? Because yeah, I know what the degrees of freedom is, but that wasn't one of the answers.
Oh, so the question they're looking for intervals, correct?
I think so.
Well, we're looking for a confidence interval.
Yes, yes, the 95% confidence interval for the difference in mean bacterial concentration.
Okay, so it's gonna be x1 bar minus x2 bar plus or minus t star times the square root of s1 squared over n1 plus s2 squared over n2, right? Or I can just use my calculator. I don't gotta do it by hand. Well, the problem is if you do it by the calculator, it does not give you the conservative value. If you do it by the calculator, it gives you the actual value. So your calculator will not actually give you the correct value here. You actually have to do this one by hand. Unless the calculator, unless the options for the multiple choice are the correct one and 3 that are so far off that you just take the one the calculator is close to. But in this case, x1 bar is 184 minus 175, that's 9, plus or minus, let's skip t star for a second because I have to look that up, but 22 squared over 7 plus 16.9 squared over 7, and then the square root of that. So that's 10.5 or so. So now I just need my t star. So I'm going to go on Google and do a T statistic calculator or table. And I have all these different tables. So I'll just pick one at random and let's take a look. So 95%. If it's 95%, that's 2.5% in each tail. So I look at 0.025 and I go to 6 degrees of freedom, and my t star is 2.44. Wow, this one's very this one's a lot of decimals. It gives me 2.446912, 2.446912, which I multiply by 10.5. So I get 9 plus or minus 25.7 or so. So I get negative 16.7 to 34.7. Was that one of the options?
Yes, it was. It was negative 16.66 to 34.66.
Yeah, okay, so to an extra decimal points, that's what it is.
Yeah, because I wasn't sure what the conservative value of the degrees of freedom was. Like, I don't remember that, so.
So we
didn't-
talked, I mean, I want to make sure, we covered the degrees of freedom formula, a very complicated looking formula that I said we never want to use. Does that ring a bell? I teach 3 stat classes, so I don't always
Yeah, I
remember every-
remember, but I feel like we didn't really like do problems that we actually did it by hand. So I guess I forgot, and like I was expecting to use it only on the calculator.
That's fair, that's fair. In that sense, you're right. We, I've always relied upon the calculator because it was always there. That's, you're right. We never actually did one where you should have done it by hand. Now, if we do it on a calculator, I'm gonna do it right now. I'm gonna go to second I'm gonna go stats, tests. We're looking for a confidence interval. This is a 2 sample T interval. My X1 bar is 184. My SX is 22 with 7. My X2 bar is 175. My SX 16.9 also with 7. 95% confidence. And I calculate, so it gives me negative 14.02 to 32.015. This is from calculator, where the degrees of freedom is equal to 11.25. And this is by hands, where the degrees of freedom is equal to 6. Now, what were the 4 choices on the multiple choice question? Obviously, there was negative 16.7 to 334.7. What were the other options?
It was negative 11.7 to 29.7,
Okay,
negative 7.42 to 31.47, and negative 18.89 to 42.89.
okay. And of course, the correct answer of negative 16.7 to 34.7. And we did in our calculator and we got this. So when you do it on your calculator, it gives you the exact value of the degrees of freedom. When you do it by hand, and we take the conservative approach where you just take the minimum of the 2, it's going to give you a wider confidence interval because you're less accurate. So I know that the true value has to be, must be the one that they're looking for. The one that they're looking for must be wider than the calculator version. It must be wider than this. The calculator version is going to be perfect, and the one by hand is going to be wider because it's a little more uncertainty. So anything that's not wider is immediately out. That's out, and that's out. Because those are not wider. Those are skinnier, whatever the opposite of wider. Wider and whatever. So that leaves 2 possibilities. And at that point, I guess one thing we can do is we can check the center of them to make sure that they're both centered at 9. If I add 34.7 plus negative 16.7 and I divide by 2, I get 9. If I add 42.89 plus negative 18.89 and divide by 2, the center of this is 12, so that can't be out. Because 9, which is my statistic, has to be right in the center. And while we're at it, this one gives me 12.025. And the other one gives me 9. Whoops. So 2 of them have a center of 9 and 2 of them don't. The ones that don't, I can throw away because the center has to be 9. And of the 2 that are 9, the value that I get has to be wider than the value of the calculator. So technically there was a way of using the calculator's value to get it, but you did have to recognize a few pieces of information. But anyway, does that make sense though? Everything I said just now. Okay, so yeah, we didn't do one, and for that, you're right, I'm sorry. But hopefully, at least in hindsight, it makes sense, the different ways you could have gotten the right answer there. Okay. Any other questions on things that we've done previously?
I always get tripped up in finding T a lot of questions asked to find T, and I use the distribution table and it would be wrong.
Well, when
And I
I
also
use,
use a calculator and then it's also wrong at the same time. Yeah.
well, do you have an example that we can look at?
Example, let me try to find one.
While you're doing that, let me just kind of take a look at the daily schedule and where we should be, because we're already about half an hour into class. I want to make sure that we cover what we need to today. So math, 140 science. Okay, so today is November 18th. And the goal today is to finish chapter 23. Start and finish 23. What was the last chapter that we did? I'm pretty sure we did 22. In fact, I know we did 22. So chapter 23 is a pretty straightforward chapter. Okay, we'll do that today. Okay, so did you find a question?
Yeah.
Is it on, you want to read it to me?
Can you pull up his question 4 on hold on.
Question 4 on,
I think it's 21 or 22. 21, yes. Question 4 on number 21. No, question 4 on chapter 21. Homework.
question 4 on chapter 21 homework. Okay, hold on a second.
I'm sorry, it's taking a long time with these questions.
It's okay. So view all. So 21 homework you said?
Yes.
And you said chapter question 4?
Yes.
This one here? This the one?
Yeah, it has the first part with the T, and the second part was.
Well, let me take a look. Let me read the question. It says, women stereotypically talk more than men do, and researchers wondered how much more. Suppose the study attempted to determine the difference in the mean number of words spoken by men or women per day. The results of the study are summarized in the table. So group 1, don't know the mean, 56, 56. We have sample means, we have sample standard deviations, and we have the standard error estimates. It's only an estimate because it's S over the square root of N, and S itself comes from the sample. We also have the degrees of freedom, 109.6851. Assume the conditions are satisfied for a 2-sample T confidence interval. First, to determine the positive critical value T for a 90% confidence interval, to estimate how many more words spoken each day on average compared to men. So T is going to be equal to X1 or XW bar minus, okay, so I can't, all right, I'll share again. What do I have? The question. So X W bar minus X M bar minus the assumed value if the null hypothesis is true. But this is the confidence interval, right?
Yeah.
This is a confidence interval. Okay, so I was doing it a different way. Okay. So the confidence interval is going to be X1 bar minus X2 bar plus or minus T star times the square root of S1 squared over N1 plus S2 squared over N2. Agreed?
Yes.
Okay. So we're looking for the positive critical value T. We're looking for this guy right here for a 90% confidence interval to estimate how many more words spoken each day on average compared to men. So give your answer precise to at least 3 decimal places. So if we take out our calculator, because the only way you're going to get it that precise is with a calculator, I'm going to do a stat test. It's a 2-sample interval, so 2-sample T interval. My X1 bar from The computer is 18443 with a 7460S. My N is 56. My X2 bar is 16576. Its S is 7871, also 56. And we're doing a 90% confidence interval. We're not pooling our results. So the calculator gives me negative 537 to 4271. Okay, that's what the calculator gives me. With me so far?
Yes.
Okay, now the margin of error, I take 4271 and I subtract negative 537 and I divide by 2. The margin of error from center to edge is 2404. That's the margin of error. And this has to equal to T star times the square root of S1 squared over N1 plus S2 squared over N2. And that, since I know what that is, I can calculate it. It's 7460 squared over 56 plus 7871 squared also over 56 and then square rooted. This becomes T star times 1449.163804. So if I divide both sides by that number, I get 2404 divided by that. It gives me T star equals 1.658887693. That's what I get from my calculator. And what they want is 1.65887. They wanted 1.65887. So we see that with 3 decimals, what my calculator gives me is close enough. Make sense? Hopefully.
That was a lot.
What was a lot? I only have like 5 lines of work there.
Okay, to me. So basically you get the confidence interval and then you divide the upper level. You subtract the upper level and the lower level, right? And then you use that value in the, I guess, T star formula.
Right. Upper minus lower is the entire difference. You got to divide that by 2 to get the margin of error.
Divided by 2, okay.
Right, and that's equal to T star times the square root of S1 squared over N1 plus S2 squared over N2. And we have those numbers, so you can plug it into the calculator and you get that. And then you just divide and you get T star.
Okay, now I know.
Cynthia, question?
I was just wondering, I know my calculator, I can find T star. So I was just wondering, the degree of freedoms, would it be, because it's in decimal, so would it be 109 or would it be 108? When I put it into the calculator.
Do you put in degrees of freedom directly?
I just do like 1 minus 0.05 because it's 90% confidence interval.
Which calculator are you dealing with?
TI-84. The one you have, I think. That's the one.
Okay, so tell me what you're pressing, because I don't have that situation, I don't think. Tell me what you're pressing from the start.
Okay, hold on, let me get it real quick.
You came to class without your calculator? Jeez, that's like showing up at a gunfight without a gun. Of course, I shouldn't talk about guns. It's a sore subject in this day and age.
So I go to second and then the distribution something.
Okay,
And then I go to T, I go 4, which says inverse T.
oh, you're doing it that way.
Yes. And then,
Okay,
and then it's
so we want a 90, how much confidence do we want in this problem that we just did?
90, I think.
Okay, so 0.90, and can I put in 109 point, whatever the number was? 109.6851, can I put that in? Yeah, I can put that in. But I don't want to put a 90% because remember, 90% is in the center.
1 minus 0.05.
Yeah, 95%. So inverse T, 95% with 109.65851. Hey, look at that. the calculator gave me 1.6588888864578. So we see the calculator is in agreement with both the answer and the way I did it. So yes, the calculator could have gotten it pretty quick.
Okay, so I don't have to round it down to 108
No,
though.
no. You put in the actual value. You put in 95. The reason why you put in 95% there is because of 90% confidence interval. We want 90% in here, but the question is, what's this point? This point has 95% to the left. That's what we're putting in. We're not putting in the area in the center. We're putting in the area to the left. So a 90% confidence interval, you put a 95% to the left of the point that you're looking for. And that point would then be this guy right here. ¿Verdad? ¿Entiende? I'm pretty sure those are right words. I took Spanish in college. I got a C, so I retook it and I got a D. So Spanish is not my strong point. I'll tell you that much. I know I cursed out my teacher. I'll tell you that much, but that's about it. Okay, so, all right. So let's do chapter 23 now that 40 minutes in. Great. It's a good thing these chapters are very small. Chapter 23. It's on comparing two proportions. Comparing two proportions. And this is the last scenario. We've done a mean and two means. We've done one proportion. Now we're doing two proportions, and that's it. Those are the four scenarios that we're covering for the majority of this class. Yes, there's one more example, which we'll do in the last week. It's a very easy example. Not small. The example takes a while, lots of computations, but the actual conceptual idea is pretty straightforward. So now we're doing two proportions. And as always, we have two scenarios to cover. We have confidence intervals and we have hypothesis testing. So the book is going to do confidence intervals first. So confidence intervals. And if you recall, for confidence intervals, oh, and before we do this very quickly, I went through all the emails because a lot of them were, extend the homework and do this and do that, and a bunch of other ones. I still have a few emails from people about attendance, where my attendance is wrong, or I didn't correct it. They came late and I didn't notice, or they had an excuse or this or that. If you still have, go please back through your attendances. If there's still an issue, just let me know. Of course, just remember, as I said before, if I let you guys out early and everyone leaves and there's a few stragglers and I say, hello, are you there? Hello, and you don't respond, and I give you a nice little buffer of time, I mark you as absent for the day. So if I have some emails every now and again saying, hey, wait, I was there. And I'm like, well, no, you left or you weren't there. So too bad. So don't email me if that's the case. So confidence intervals. So what's the confidence interval? So you have sample one. And from sample one, of course, you have size N1. And you have number of successes X1. And because of that, you have your sample proportion P1 hat. And then you have sample number 2, and you have sample size N2, number of successes X2. And because of that, you have sample proportion P2 hat. And the question is, what is P1 minus P2? Not what is P1 hat minus P2 hat. That's a silly question. I know P1 hat and P2 hat. They come from my sample. I don't have to question them. I'm questioning the true values, P1 and P2. What's the true difference between them? So my confidence interval is P1 hat minus P2 hat, plus or minus Z star, square root of P1 hat, 1 minus P1 hat over N1, plus P2 hat, 1 minus P2 hat over N2. And the question is, when am I allowed to use this? If you recall, for one proportion, I had to have the number of successes and the number of failures both greater than or equal to what number? You guys recall? For one proportion, number of successes and number of failures must both be greater than or equal to what number? 10. That's right. For one proportion, it was both of them had to be greater than or equal to 10. If it wasn't, or if either of them was not greater than or equal to 10, what was my fallback scenario? What was my fallback if they weren't, if there wasn't 10? What did I do in that case? No, I think you're talking about something else. You're talking about the t-test and its robustness and it being okay with a sample size of 15 or a sample size of 40. But we're talking about lower, not higher. What if I don't have 10 successes or failures? Then I would use the small sample confidence interval. Well, the same thing goes here. Only use this version, the large sample confidence interval, if there are greater than or equal to 10 successes and failures in each sample. So only use this version, the large sample confidence interval, if there's at least 10 successes and failures in each sample. What if there isn't? What if there's not? What do we do in that case? Then use the small sample confidence interval. Of course, when are we allowed to use the small sample confidence interval? What is the condition which allowed us and with one proportion to use a small sample confidence interval? Anyone recall? Should have like a bullet point note sheet or something with all the conditions for all the cases, for all the different scenarios. But you could use a small sample confidence interval if each sample has at least 5 elements. So I get to use a small sample confidence interval for 2 proportions if each of the samples has at least 5 elements. And what is it? What is the small sample confidence interval? Do you guys recall what it was for one sample? We didn't use P1 hat and P2 hat anymore. What did we use instead?
P twiddle.
Yeah, P1 twiddle minus P1 twiddle plus or minus Z star square root of P1 twiddle 1 minus P1 twiddle over N1 plus P2 twiddle 1 minus P2 twiddle over N2. And what is P1 twiddle? Sorry, it's not N1 and N2. I always make that quick mistake. I just go too fast. What is P1 twiddle and P2 twiddle? And what are my new denominators? So if you recall, for one confidence interval, what did we add to the top and what did we add to the bottom to get P1 twiddle? Anyone remember what we added to top and bottom to get P1 twiddle?
1/4.
We added 4. In this case, because there's 2 samples, we're going to add 2 to each one. And with one sample, we added 2 to the top. So what do you think we're going to add to each top in this one? How much do I add? No, it's not 4. It was 2 in the last case. It's gonna be 1 for a total of 2. Remember that in both cases, we had a total of 4 to the bottom and a total of 2 to the top. With one sample, it's just you add 2, you add 4, you're done. With 2 samples, you split it in half. You add 1 to the top and 2 to the bottom for each of the 2 samples. And my denominators follow suit. We just add 2 to each. I'm not deriving these formulas. To be honest, I'm not even sure why they work so well. I've never derived them. I just know that they say to do it this way. But I don't know why they say to do it this way. I just trust them because they're pretty smart. So now we have our confidence intervals. What about hypothesis testing? So now the other half of the coin, hypothesis testing. What is our H naught going to be for 2 proportions? What's our H naught going to be?
P equals PO.
Say again, please.
P equals PO.
But we have 2 samples here, not just 1. Right, we're comparing 2, remember the title of the chapter, right? We are comparing 2 proportions. If I'm looking at 2 different proportions, what do you think I want to know about those 2 proportions? Are they equal? Or is their difference 0? Now, in general, beyond the level of this course, I might be interested if their difference is anything. Is P1 minus P2 equal to 0.3? But in this course, it's always going to be 0. The null hypothesis is claiming that P1 minus P2, the difference between the proportions is 0. What are my 3 alternatives going to be?
Less than, greater than, or equal to, or not equal to.
Good. Less than 0. Greater than 0. And not equal to 0. Where would I reject the null hypothesis in each one of the 3 cases? Where would I reject in the first case?
The left side,
The left side. Where would I reject in the second case?
the right side,
And how about the third case?
on both sides.
On both sides. Of course, your calculator does most of the work here. So what we do is we compute our Z statistic, which you can kind of see from the confidence interval is P1 hat minus P2 hat minus the assumed P1 minus P2, which is 0 if the null hypothesis is true, divided by, but now actually it's kind of interesting. If you look at the confidence interval, then we have the P1 hat, we have the P2 hat, they're different. But if we assume that null hypothesis is true, then P1 and P2 are the same. And we want to use that. And we do that by combining them together And again, not worrying about the details. It's just a matter of memorizing or writing it down and using it. We use p hat 1 minus p hat 1 over n1 plus 1 over n2. Where p hat is equal to what?
Isn't it where you go like x minus 2 over like something minus 4?
No, but thanks for playing.
X over N.
X over n is p1 hat for the first sample. X1 over n1 would give me p1 hat. And x2 over n2 would give me p2 hat. But now I'm looking for just p hat with no subscript. So how would I find p hat? The proportion of successes if the null hypothesis is true. If the null hypothesis is true and they have the same proportion, then why divide them into two different samples? Just pool it all together. The total number of successes divided by the total number of failures. Trials. Total number of successes divided by the total number of trials. It's not x1 over n1 or x2 over n2. It's the total number of successes, x1 plus x2, divided by the total number of trials, n1 plus n2. So p hat in this case is x1 plus x2 over n1 plus n2. Again, your calculator knows all of this. Your calculator will just automatically do it. But as the quiz showed, sometimes you might have to be doing things by hand. So you should know what these formulas are. So has everyone written everything? If so, I'd like to do a couple of examples to demonstrate.
What's the second part of the numerator? It's the minus what?
This part here?
Yeah.
Basically minus 0. It's minus p1 minus p2, but p1 minus p2 is just 0. Because under the null hypothesis, that's what p1 minus p2 is. P1 minus p2 is 0. In a more advanced class, p1 minus p2 wouldn't be 0, and you'd actually include that. So let's do a few examples to illustrate this in action. Okay, so here's an example from the back. It says the following. While nearly all toddlers and preschool-age children eat breakfast daily, consumption of breakfast dips as children grow older. The Youth Risk Behavior Surveillance System, the YRBSS, monitors health risk behaviors among US high school students. In 2017, the survey randomly selected 4,031 ninth graders and 3,396 12th graders and asked them if they had eaten breakfast on all 7 days before the survey. Of these students, 1,536 ninth graders and 1,090 12th graders said yes. Do these data give evidence that the proportion of ninth graders who eat breakfast daily is higher than the proportion of 12th graders eating breakfast daily? Is the proportion of ninth graders higher than the proportion of 12th graders? Well, first, let's label stuff. What should I label these 4 numbers?
Is it like x1?
Which one is x1?
The 4,031.
And what would the other number beneath it be then?
Oh,
I'm just curious. No? Change your mind? Take it back? Regret ever opening your mouth at all?
yes.
So someone help me out. Are these four numbers?
4,031 is N1, and then 3,096 is N2, 1536 X1, and then 1090 X2.
Well, damn. Okay, so we have our sample sizes and we have our number of successes for both scenarios. So we'll do both a hypothesis test and we'll also do a confidence interval and we'll see if they agree with their conclusions. What is the null hypothesis here? What are we trying to establish? Do these data give evidence that the proportion of ninth graders who eat breakfast daily is higher than the proportion of 12th graders who eat breakfast daily? What would my null and alternative hypotheses be?
Can you say that problem line again?
Sorry, I didn't hear that.
Can you say the problem again? That
Sure.
you just said?
It says, do these data give evidence that the proportion of ninth graders who eat breakfast daily is higher than the proportion of 12th graders eating breakfast daily?
So would it be the null hypothesis be mu is equal?
Sorry, do you say mu?
I mean p hat.
Well, so again, it's very important. Hats, p hats, come from your samples. Information from your samples should never appear in your hypotheses. Your
Would it just
hypothesis,
be-
huh?
Would it just be p then?
Which p?
I don't know.
Well, there's two samples, so which one are you talking about?
Oh, p1 and the p2.
What about P1 and P2? What does a
I don't
null
know.
hypothesis? What does
I
a null
know it's-
hypothesis claim, huh?
I know, is it gonna say like it's equal to, and then you put 1090?
1,000, no, remember, the information from your sample, those four numbers never appear and shouldn't appear in your null hypotheses.
Okay, then never mind. I'm just gonna,
No, I want you to keep trying. I want you to keep trying. Okay, no, 100%. Don't worry, but no one's gonna remember tomorrow that you got something wrong today. I mean, I'll remember, but nobody else will remember. So the null hypothesis is that P1 minus P2 is 0. Yes, that there's no difference between P1 and P2. Whatever they might be, I don't know what they are. I don't know what they are. I'm claiming that there's no difference. And I'm testing what? What is my alternative going to be? What do I want to see if there's evidence for?
P1 minus P2 is less than 0.
Well, I'll read the question again. Do these data give evidence that the proportion of ninth graders who eat breakfast daily is higher than the proportion of 12th graders eating breakfast daily?
Okay, then greater than.
Greater than 0. We're looking to see whether or not the evidence supports the fact that P1 is greater than P2. That's what we're checking. Do the data provide evidence of this or not? But notice what does not appear in my hypotheses. Sample information. I'm going to use my sample information to conclude something about P1 and P2 and whether the null hypothesis or the alternative hypothesis is the one that I'll be not rejecting or rejecting, whatever the case may be. So where do I go from here? What do I do now? Anyone?
Don't you have to find the p-value?
We are going to find, well, yes, I mean, the calculator is where we go. In an effort to find the p-value. So which part of the p-value am I going to go to?
The stat test and then one prop z test.
The stats test, and then a one proportion z test.
Wouldn't it be two?
Well, hey, I told you to keep trying. I knew you'd get it. Yes, the two proportion z test. We're dealing with two proportions here. So go put everything in. What do you get? So what do we get? P equals. So Luis, what you wrote there, there's lots of P's here. So which one are you telling me is 0.3537? 35357. The last hats. Right? There's P1 hats, there's P2 hats, there's P hats, and there's P on my calculator. Which of those things is the one that I care about? And Cynthia's right, it's P, which is essentially 0. Doesn't say 0. What does P say? Let's try to be accurate. What does P say? Someone read to me P. Yeah, P is 0.0005673426, whatever. So P is extremely small. P is essentially 0. And if the null was low, sorry, crap. If the P value is low, the null. Didn't I give you this line last time? This is my first time saying it.
Let's go.
The null must go. The P value is low, the null must, huh? If the P value is low, the null must go. If the P value is high,
The null will stay alive.
okay, that's not the worst. It's not horrible, stay alive. I actually kind of like that one. The null must stay alive. I like that, but let's rhyme with high. If the P value is high, I didn't give you this before, something fly. Reach for the, woo! Reach for the
I only
sky.
wrote the first half in my notes. Oh, I don't have that part.
Reach for the sky, baby. That's what I'm talking about. No, if the null is high, let the null, sorry, God damn it. If the P value is high, let the null fly. Damn, but I like what the null should stay alive. I kind of like that one too. I kind of like that. I gotta give you that one. We gotta come up with a better rhyme than fly. High fly guy, high my why. Oh my. No, I don't know. I got nothing. The null does not die. The null does not die. Hello. Woo, that's a good one. The null does not die. That's actually pretty good. Anyway, so what do we conclude in this case? Are we going to reject or not reject the null hypothesis here?
Reject.
We reject. We reject with high confidence. High confidence. I mean, a p-value that low, essentially, it will never happen by chance alone. Which means the fact that it didn't happen makes me seriously question the null hypothesis, which says 9th graders and 12th graders eat the same amount. So I can speak for myself. I'm so tired when I get out of bed in the morning. I am so exhausted. I'll stay in bed to the last second that I can and still manage to make it to school on time. And I'm usually cutting it to like within a minute or two. So I don't have time to eat. Of course, then when lunchtime comes around, I have to make up for it and have like 3 meals because I might not have dinner. So I have to have my breakfast, lunch, and dinner. And then I'll have my dinner later because I always have my dinner. So it's really, it works out well. Anyways, so that is the null hypothesis approach. Now let's go ahead and do the confidence interval approach. Let's find a confidence interval for P1 minus P2. What would my confidence interval be? Where would I go? How would I find a confidence interval?
When you do the 2 sample interval,
Sorry, what's it called again, please? Hey, you in the background, stop talking when she's in class.
I know, I'm trying to tell. You would do,
I'll give him a piece of my mind.
you would do a 2 sample,
The 2 what?
2 interval, 2
Sorry,
something.
sorry, the
interval.
what? The 2 what?
I don't know. It's
Just
exactly.
read it. Read it.
No, I don't have the calculator with me.
Oh, well, that explains things. It's the 2 prop Z.
You don't do the
Interval.
interval one?
It is.
9? Oh, yeah, okay.
Right, the 2 proportion Z interval. And do it 90% confidence. Do 90% confidence. So what do we get? What is my 90% confidence interval for this scenario? So I get 0.04186 to 0.0783. It's exactly the same thing I get. Awesome. And therefore, what is my conclusion? Why do I reject the null? What's the reasoning behind that? Yes. Yes, 0 is not in my confidence interval. There's no 0. 0 is not an element of my confidence interval. That's a little script E stands for is inside of. 0 is not inside of my confidence interval. So at 90% confidence, I would never claim the difference is 0, but rather only greater than 0. Yes?
Can you say that thing again so I can write it down?
Yeah, okay. If the P value is low, the null must go. If the P value is high, the null does not die. I decided it's my favorite one.
Thank you.
No problem. The null does not die.
It must die? Is that
No, the null does not die.
not die if it's okay?
Let it fly. Okay, maybe that's better. I don't know. The null is right. Oh my, no, that doesn't work. I like corned beef on rye. No, that doesn't make any sense. Lie. The null does not lie. No, I'm not sure that works. No sigh. So many things rhyme. It's so hard to pick one. All right. Any questions on this? 0 is not in the confidence interval. Therefore, we're going to reject the null hypothesis that it's equal to 0. How can I say it's equal to 0 if 0 is not in there? Right? Yeah. Let's do another one. Let's do one more. The Abbasidarian Project was a randomized controlled study to assess the effects of intensive early childhood education on children who were at high risk based on several socio-demographic indicators. The project randomly assigned children to a treatment group, which was provided with early educational activities before kindergarten, and the remainder to a control group. A follow-up study interviewed subjects at age 30 and compared college graduation rates, and this is what they found. There were 2 groups. The first one, this is the treatment group. These are the ones who got, actual education, and these ones who sat around doing nothing all day. Story of my life. Sample size 52 and 49. Number of successes 12 and 3. And that's it. That's the info. What the freak? What did I just do there? Oh my God, there's like 2 of them now. What?
You didn't know you could split your screen?
What? No, I didn't know I could split my screen. How do I split? This is crazy. How do I unsplit it though?
Move it to the middle, little middle bar right there. Move it to the side.
Oh my God, there it is. Wow. Shit, I just hit it again. Crap. Have those 3 dots always been there? Because I've been hitting them like crazy lately. I don't know. Anyways, so here's my info. So the question is, does early treatments or education increase the proportion of earning a degree by 40? Does early treatment, early education increase the proportion of earning a degree by 40? That's the question. So let's do a 90% confidence interval. And let's do it by hands because, I don't want to have any more complaints. Oh, we never do it with my hands. So let's do it by hands. What do I do first?
I literally just got my calculator though.
Yeah, I feel like it's easier on the calculator. Maybe it's more confusing with hand. I don't know.
Really?
No, I'm just lazy. Let's do the calculator.
You can do it though, it's fine.
Do the computer high five. That's what I'm talking about. No, don't break your computer. That's crazy. Okay, so 90% confidence interval. Okay, at least give me the formula for it. What's the formula for it? Hey, we'll use a calculator. What the hell? I don't want to go against like public pressure. but let's at least write the formula down. What's it gonna be?
P squiggly line. I don't know the name.
P1 twiddle.
Yeah, P1 twiddle minus P2 twiddle.
Why are we using twiddles, by the way? Why not the hats?
Because we don't know the. Oh no, wait. I don't know.
Well, you chose it.
Is the twiddle for small?
The twiddle is for the small sample. What makes this a small sample? And I mean, we call it the small sample, but what makes the right choice to use this version versus the other version? Okay, great. There you have the calculator. Now we just gotta, remember stuff. So if I go back here where I wrote it down, because I did write it down today. I think I wrote it down. That would suck if I didn't. Did I do it?
It's less than, I mean, greater than or equal to 10.
Yeah, so it's all here. We use the large sample version if there's greater than or equal to, oh, Diana wrote it, I didn't see it. If there's greater than or equal to successes and failures in each sample, otherwise, we just want at least 5 in each sample. So do we have greater than or equal to 10 successes and failures in each sample here? No, sirree, Bob. We only have 3 in the second one. So I can't use the large one, but all is not lost because I have sample sizes of at least 5. So I can use the small sample, which is the P1 twiddle minus P twiddle, plus or minus what?
Wait, so just for clarification, if 3 was greater than 10, we would use the large?
That's right.
Okay, got it.
That's right. So P1 twiddle minus P2 twiddle, plus or minus what?
Z star.
Z star.
Square root of P1 twiddle. Oh wait, no, yeah, no. 1 over N1 plus 2 time. It's a lot.
P1 twiddle 1 minus P1 twiddle over N1 plus 2, and P2 twiddle 1 minus P2 twiddle over N2 plus 2. That one?
Yeah, that one.
That's the right one. Now, what is P1 twiddle?
Is it 52?
So you're saying P1 twiddle is just 52.
Oh wait, no, because twiddle you have to do that. Something to.
Yes, you gotta do something. So first, what's P1 hats? Let's start there. What's P1 hat equal to? As a fraction, what's P1 hat? Anyone? What is P1 hat as a fraction?
X1 plus X2 over N1 plus N2.
Just one, no, P1 hat, now P1 twiddle. It's just X over N. This is 12 over 52. P1 hat is just 12 over 52. Number of successes over number of trials. P1 twiddle, we changed 12 and 52. What do we change 12 till? What do we do to it?
Add 2.
Add 1. Remember, for the 1 proportion, we add 2 on top, 4 on bottom. For the 2 proportions, we do 1 on top, 2 on bottom. But we do it for each one. Is this ringing a bell? Yes, no, maybe so?
You said for 1 proportion, you do
2
2
on top, 4 on bottom.
And then for 2, just 1 on top.
Well, you're still doing 2 on top, 4 on bottom, but you're splitting them into the first sample and the second sample. So each one gets 1, 2, 1, 2. So what do we get here for the confidence interval? We get 13. Oh, well, actually, now we can go to my now we can go to the calculator and do stat. We're doing a confidence interval. It's a 2 proportion Z interval. How many successes are there? What's my X1?
Wait, 52 and 49 are sample sizes?
Yep.
And so 12 and 3 are the sample?
They're the number of successes in my sample.
Okay.
Sample size, and these are the successes. I didn't know how to spell it, so I just kind of scribbled it a little bit. Lots of S's and E's all over the place.
So wouldn't X, you said X1,
Mhm.
would that be 13?
Yes, it would. And what's my N1?
54?
Yes. And then X2. Four and N2. 51. So what is my confidence interval going to be? No.
Professor, you went to 2 sample Z interval?
2 proportion
Proportion, okay, right.
Z interval. So what do I conclude? And why? What do I conclude and why? What was C? The confidence, you mean?
Yeah.
It's a good question. If only you didn't say it right there in the middle on the left side.
Oh, okay.
Reject null, since 0 is not in the confidence interval. Reject. The null must go.
So in the problems like these, when you do HO and HA, is it always going to be equal to 0?
The null hypothesis always, always, always gets the equal sign.
But 0.
In this course, yes.
Okay.
In a more advanced course, no. And Cynthia, the question was, how did I get X1 and X2? It's the numerator of my twiddles. So you take the number of successes, which is 12, and add 1, so you get 13. That's my X1. And you get 4, that's my X2. Because for the small sample confidence interval, you add 1 on top. So your X goes up by 1 and so on. Okay. So we finished chapter 20. Shit, what chapter is this? 22, 23? What do we just finish?
23, I thought it was.
23. Wow. So we only have a couple chapters to go and then we're all done. Oh, how nice. So let's take a look. We just finished week 12. We have a Tuesday in week 13. And then we have week 14 and week 15. So we have 5 days left. I think we got a quiz in there too, don't we? let me, where is this thing? Where's the, let's take a look. So we have Tuesday, chapter 6 is the goal on Tuesday. And then we have Tuesday, and then we have the comprehensive quiz is Thursday. So the next test, comprehensive quiz number 3 is on December 2nd. That will cover chapters 20 through 23. 4 chapters. Basically, it's all hypothesis testing and confidence intervals, just lots of them. And then the last week, it says here, review, before we have our common comprehensive final on Saturday, December 18th. How fun is that going to be? So the final will be, definitely a final will be cumulative. Yeah, 100%. If it wasn't cumulative, it'd be like in 2 chapters, because we'll have been tested on everything else. So yeah, no and oh, sorry, are you saying no, like you will not allow it, or no, like you accept it, but you just are not happy about it? Because no can really, like, no, it's like a Neo in the Matrix type thing. No, like he's altering reality. So, it all depends on how you're viewing it. I don't know. Anyway, I'm tired. I gotta go lie down to my next class. So too much to remember. Unfortunately, it's not about remembering. It's about understanding. If you understand it, you don't have to remember. It's just, you get it. So it's there. You've internalized it. It's inside of you forever. You'll never forget. It's like 1 + 1. You don't say, I don't remember 1 + 1. You know 1 + 1. It's in there. That's the goal, which is pretty much impossible to get in any course ever in the history of time. So it's an ideal, but I hear you. It's a lot to remember, which is why you get notes probably. I know you do in my other class, but I'm pretty sure you do in this class too.
Really, like open notes?
I think so. I have to ask.
Is it like one sheet you can write stuff on?
I think so. Like I teach so many different classes and they all have different policies that I sometimes I forget what goes to which, but I'm pretty sure it's open notes.
Well, can you figure that out so I can?
Oh, for Leanne, for you,
Yeah.
you got it. If it was anyone else, I'd say, you know what? No, but because you asked, I'm going to do it.
Thank you.
You're welcome. All right, everyone. So I'm going to stop recording now. Shout out Leanne. Boom. That's what I'm talking about.